Good day everyone, I'm Yong. I'm going to present the paper Prediction of Conversion to Alzheimer's disease using 3D-DWT and PCA. My co-authors are Prof. Shafry, Rahim, and Dr. Tunku. What is Alzheimer's disease? Alzheimer's disease in the short form is AD. AD is a degenerative brain sickness. The patient suffers AD will undergo atrophy of the brain due to the death of the neurons. As shown in the image, it is a huge difference between healthy brain and the brain of the patient suffers AD. As a result, AD patients will have cognitive and behavioral impairment. The patient faces the problems such as memory loss, difficulty in reasoning, the change of emotion, even they might face the difficulty in conducting their daily routine. So it is very important to predict the conversion to AD. There are three main stages in the development of AD. Normal control (NC) refers to the patient remain as healthy. More cognitive impairment (MCI) is a stage between the expected cognitive decline of normal aging and the more serious decline of dementia. For those remains in MCI after a period of observation is called stable MCI (SMCI). For those convert to AD after a period of observation is called progressive MCI (PMCI). Therefore, it is very important to differentiate the PMCI patient from SMCI patient to provide a better treatment for the patient. According to previous work, for cell-based morphometry, VBM was one of the widely used approach in AD classification. Through VBM approach, it proved that the grandmother alternation is consistent with the neuropsychological test. The neuropsychological test will be conducted to the patient who is suspected to have cognitive impairment to measure how well the patient's brain is working. The abilities tested include language usage, attention, processing speed, and more. Besides, the reduction of gray matter in healthy patient who faces cognitive impairment is greater than the healthy patient who remains normal cognitive. Hence, this study used VBM approach to compare the brains of the subjects. And gray matter is the feature used in this study. However, VBM faces the challenge of high-dimensional data. 3D MRI image consists of around 2 million features. Therefore, it requires feature extraction before classification to extract significant features and to reduce the number of features concurrently. By adopting 3D-DWT and PCA, it had improved the classification result. However, the combination of 2D-DWT and PCA dropped the classification result compared to use 2D-DWT alone in one of the literature. The contradicting results may due to various reasons, such as parameter selection in DWT and the number of the principal components we selected after PCA. In terms of the classification, support vector machine SVM and deep learning approach were widely used as the classifier. However, the parameter tuning of deep learning approach is challenging. There is a lack of guidelines on determining the layers in between and the number of hidden layers. Therefore, this study adopted SVM as the classifier. In view of the previous study, the goals of this study were set to first, to identify the suitable level of decomposition and wavelength for DWT for AD classification. Second, to find out the strength of DWT and PCA on the prediction of conversion to AD. So experiments were conducted to test the well-known wavelengths and different levels of decomposition. The proposed model for the prediction on conversion to AD is shown in this figure. The input image was 3D image, which underwent preprocessing before feature extraction, such as gray matter segmentation and spatial normalization. Different subjects have different brain size. As the brain images are spatial normalized, it can be used for further analysis. Preprocessing was run through a conventional software, CAT-12, by using default parameters. 3-level 3D-DWT with hardware flat and PCA were the proposed feature extraction methods, and SVM performed binary classification. DWT is primarily used in signal coding, which is a time-frequency analysis. It captures both frequency and location information. It can be used in data denoising, data compression, feature extraction. It also can be used in image processing. The image is treated as signal and edges, which provide the frequency information to the algorithm. The 3-level 3D-DWT used in this study is illustrated in this figure. 3D-DWT involves decomposing the image in rows, columns, and slice direction. The image will go through low-pass filter and high-pass filter. The low-pass filter was written as capital letter L, and the high-pass filter was written as capital letter H in this figure. DWT is a downsampling process, and the downsampling process was drew with an arrow. 3D-DWT will produce 8 subbands as shown in the image. LLL actually is the output of the image that passed through 3 low-pass filters. LLH is the image that passed through 2 low-pass filters and 1 high-pass filter. This interpretation can be used to other subbands as well. This study used half wavelet as a wavelet filter for 3D-DWT. It is derived from the half matrix. The half matrix for 1D-DWT is given in the equation. The first column produces approximation coefficient, and the second column produces detail coefficients by finding the difference of the pixel values. 1 over square root of 2 is a normalization constant. The 3D-DWT can be obtained through performing 3 types of 1D-DWT in row, column, and slice direction. Therefore, LLL can be obtained through the following equation. This study only tests the LLL subband as the features to fit in classifier. Therefore, only the equation of LLL subband is provided in the paper. After getting the approximation coefficients of the data was transformed to a long feature vector to implement PCA. PCA finds the lines that maximize the variance of the data to obtain the minimum representation of the original image. The second line is perpendicular to first line, and it goes on to third, fourth, and the rest of the lines. By projecting the data points to the lines, we obtain the transformed data called principal components. The first principal component has the largest variance of the data, and the variance goes down to the last principal components. In order to find the direction and magnitude to project the data, eigen decomposition is the classical way. However, it might face accuracy loss due to eigenvalues are sensitive to perturbations. Therefore, this study implemented singular value decomposition (SVD) to replace eigen decomposition. SVD is numerically stable in computation. The dataset used in this study were collected from any database, which was widely used by many researchers. The datasets were collected in 4 time points, which were 24 months before stable diagnosis, 18 months before stable diagnosis, 12 months before stable diagnosis, and during stable diagnosis time point. The dataset collected during the stable diagnosis time point means the patients have been confirmed in which stage of the disease or remains as healthy after 2 years of follow-up. Each dataset consisted of 50 NC patients, 50 SMCI patients, 50 PMCI patients, and 50 AD patients. The images obtained were T1 weighted MR images. This study conducted binary classification to predict the conversion to AD. Therefore, the different groups of patients were categorized based on the condition of the disease. NC and SMCI patients were grouped together as healthier patients. PMCI and AD patients were grouped together as sick patients. Factor cross-validation was employed in this paper to ensure good generalization on the model. Each dataset was divided to 5 subsets for 5 times randomly. Each time, 4 out of 5 subsets were treated as training set, and the remaining subset was treated as test set. Accuracy was the measurement metric in this study. The model was required to correctly identify sick patient or correctly reject healthier patient. The experiment on the selection of parameters for DWT was conducted by setting the initial level of decomposition to 2, and the criteria to stop the increasing of decomposition level was the dropping of classification by using most of the wavelengths. The wavelengths tested in the experiment were half, dB2, dB4, SIM2, and SIM4. For the classification results obtained by using two-level 3D-DWT and PCA, it was noticed that the accuracies obtained by different wavelengths were similar for the datasets corrected near to stable diagnosis. In contrary, the classification results were 2 to 3% difference for the dataset corrected at the earlier time points. In two-level 3D-DWT, SIM4 achieved the best results compared to other wavelengths. Then we continue to test 3-level 3D-DWT. Wavelength and SIM4 both achieved higher results compared to the highest result in 2-level 3D-DWT, except on the dataset collected at time point of 18 months before stable diagnosis. It was 1% lower in 3-level 3D-DWT when we look at the lowest mean accuracy. For example, wavelength, the lowest mean accuracy is 79. dB2, the lowest mean accuracy is 78. So, by looking at the mean accuracy, wavelength obtained higher result compared to the other wavelengths, which was 79%. The results by using 4-level 3D-DWT were dropped significantly on most of the wavelengths except dB4. However, it did not show improvement when compared to 3-level 3D-DWT with high wavelength. That is the reason for us to stop continue to testing 5-level 3D-DWT. As a result, this study proposed to use 3-level 3D-DWT with high wavelength and PCA as feature extraction. The possible reason for dropping the classification result is the omitting of significant features. DWT is a find-to-cost method. It is a trade-off relationship between compression ratio and the features to be kept. The image details will be eliminated along each level of decomposition. Now this is the output of 3-level 3D-DWT. DWT involved downsampling process, therefore the size of the image was reduced to half on each dimension compared to previous decomposition level. The number of features was reduced from around 2 million to around 4,000 through 3D-DWT, and it was further reduced through PCA. The output of PCA was 159 principal components. It is impossible to benchmark with the previous work due to different features and different populations that were used in the studies. Therefore, we also compare different models to prove the strength of the proposed model. According to the previous work, the combination of 2D-DWT and PCA dropped the classification result. Our result was consistent with the previous study. 2D-DWT did not manage to keep the spatial information on 3D image. On the other hand, 3D-DWT obtained 2% to 4% higher compared to use PCA alone, except on the dataset collected at time point of 18 months before stable diagnosis. Even though this is an exception, but 3D-DWT still improved the classification results in overall. In conclusion, the proposed 3-level 3D-DWT with high wavelength and PCA managed to extract significant features for AD classification, and it is worth to note that all principal components obtained from PCA was used in this paper, which was 159 features. The reasons of the dropping of the results when adopting PCA after DWT in previous work might due to the number of principal components be selected. It was not stated in the previous work, but it was noticed that the feature selection caused high sensitivity issue. For the results, We also noticed that the prediction of the conversion to AD is more challenging on the datasets collected in earlier stage of the disease compared to the datasets collected at time point which are near to stable diagnosis. Therefore, more attention shall be focused on the early diagnosis and the prediction of conversion to AD to provide better treatment to the patients. The additional data such as age, gender, and neuropsychological tests can be included in future work to boost the classification results. So this is the end of the presentation. Thank you for your attention.